Hello again. On this lecture, I'll describe what are the topics covered on this course. I also try to point out how the contents of this course are related to some other courses that are offered by our department. First, about prerequisites, stuff that you should already know. So, prerequisites. Familiarity with Python coding is required. All the code is in Python and using the standard Python libraries. You should also have a solid understanding of general probability theory and linear algebra, especially matrix operations. If you feel like you could use a refresh on these topics, there is a very good and free resource book, Mathematics for Machine Learning. You can download it from this link. Our Introduction to Deep Learning course covers the basics of deep learning using Keras and TensorFlow, so you should be familiar with those. But you can of course refresh your knowledge on these by reading chapter 2 of this textbook. What comes to generative modeling, no prior knowledge is assumed. The first part of the textbook is called Introduction to Generative Deep Learning, or Introduction to Deep Generative Modeling, if you wish. And the first part consists of 2 chapters, one about generative modeling and another about deep learning. And we start by following the first chapter, generative modeling. There we define what this generative modeling is all about. Some of the key concepts that are common and important to all generative models are illustrated using a toy example. We also lay out a taxonomy of generative model families or techniques, which is useful to understand the similarities and differences of different modeling approaches. We will skip the textbook chapter about deep learning. You should know the basics and how to build and train multi-layer networks and convolutional networks. The second part of the textbook, called Methods, makes the core of this course. Let's take a brief look what these methods or key techniques are. So, key techniques for building deep generative models. And the first one is variational autoencoder, or VAE for short. What are those? Autoencoders learn to compress high-dimensional input data, like a computer image, into a lower dimensional latent representation. And not only this, but also uncompress or reconstruct the original data from its latent representation. The goal in the training of an autoencoder is to minimize the difference, or more scientifically, the reconstruction error between the original input and the reconstructed output. Variational autoencoders are an extension of the previous idea, the basic autoencoder. They aim to learn instead of a direct encoding a probability distribution in the latent space. We will learn what these VAEs are and see how they can be used to generate images. In our example case, images of human faces. And moreover, morphology or morph between images, faces, morph one face into another gradually by operating not on the pixels of the image but in the model's latent space. Next in the list is generative adversarial networks, or GANs for short. What are they? GANs consist of two neural networks, a generator network and a discriminator network. Generator, as the name says, generates new data samples, or call them fakes, simply from random noise. And the discriminator network evaluates these generated samples and determines whether they are real or fake. The generator and discriminator are trained together in a competitive game. The generator tries to create samples that are very similar to the real data. One cannot distinguish them. While the discriminator naturally tries to correctly identify which samples are fake and which are not. You can think that these two networks are opponents or adversaries of each other, hence the name. We will learn what these GANs are and how different variants and improvements of the basic idea, like deep convolutional GANs, conditional GANs and Wasserstein GANs, can be used as image generation tools. Then we have autoregressive models. Roughly described, autoregressive models are statistical models that predict future values of a time series based on their own earlier predictions. That's where the auto comes from. The, let's say, old school deep learning tools for this purpose are recurrent neural networks like the so-called long short-term memory networks, LSTMs. Nowadays the transformer architecture has largely surpassed them. Recurrent neural networks and LSTMs are part of our Introduction to Deep Learning course, so they are discussed only briefly on this course. What we will discuss more is quite an interesting idea that autoregressive models were originally developed for one-dimensional data like written text, but it can also be applied in higher dimensions. And we will see how a technique called pixel CNN can be used to generate images using autoregressive methods. The next family of models is called normalizing flow models. Normalizing flow models learn to map a simple probability distribution like the standard normal distribution, to a more complex target distribution. Furthermore, this mapping is learned in such a way that it is invertible. You can go both ways, from simple to complex and from complex to simple. So this invertibility property has several beneficial consequences, as will be seen. We will give a theoretical explanation of these normalizing flow models and a practical example where we generate images using a model called Real NVP. For the curious, NVP stands for non-volume preserving. And the next one is called energy-based models. Energy-based models define a probability distribution using so-called energy function, which measures the compatibility of the underlying model and the given training examples. The worse the compatibility, the higher the energy, and the lower the associated probability. We will learn how these energy-based models can be trained using a tool called contrastive divergence, and how one can sample from these models using so-called Lanswan dynamics. Then we have diffusion models. Diffusion is what happens to a spoonful of sugar when you pour it in your coffee or tea. It spreads out and gets disordered. Physically, it means the movement of particles from a region of higher concentration to a region of lower concentration. Mathematically, you could think that diffusion is the gradual addition of noise to data until the data becomes completely random. Diffusion models learn to generate data by modeling the reverse process of diffusion. Perhaps they should be called anti-diffusion models instead. We will give a practical guide how to build diffusion models. In particular, text-to-image generation models. The example models called DALE2 and Stable Diffusion were state-of-the-art perhaps when the textbook was written, but as mentioned, the development in this field has been very rapid. These 6 key techniques make the core of this course. The textbook also has a third part called Advanced Applications, but there's only so much material one can fit into a course of 5 credit units. So they are considered, if at all, only briefly. However, I strongly suggest that you take a look into these remaining chapters yourself. For example, they are all good candidates for your project course topic. So first there is stuff about transformers. I would like to point out that the transformer architecture is presented in detail on our department's course called Deep Learning in Human Language Technology. So if you want to find out about those, take that course. And then there are several advancements on this GAN, style GAN, vector quantification GAN, and so forth. They are discussed. For music lovers, there is a chapter about generating music. I think it's in MIDI file format, but multi-voice compositions using GAN technology here, MuseGAN. Then quite interesting world models, how to build synthetic worlds for reinforcement learning systems to try out different strategies instead of going to the real world. And finally, discussion about multimodal models which combine techniques from different approaches. So please take a look in these as well. Thank you. Meet you again.